We've updated our sensitivity analysis to let us see the results of multiple different initial concentrations in our first order decay model. The way we did that was to define a vector of initial concentrations and then write a loop to apply each value in that vector each time through the loop, and then we collected each set of results as an element of a list that we created before the loop, and then we filled in each element of that list each time through the loop. So we can do the same thing if we want to consider not only how the initial concentration changes, but also how the rate coefficient changes. What we have here then is a factorial combination where we want to see the results of each combination of a given initial concentration and then some combination of rate coefficients. And to do that, we'll need something similar in terms of a vector of rate coefficients instead of a single value. So I'm going to add an s to this, call it rate coefficients. And I'm going to say, oh, well, let's have a value that's below 0.1 to see what that does. Let's maybe call it 0.05, and then have a value above 0.1 to see what that does. And I'm going to call this one 0.2. So we now have three different rate coefficients. We just have to figure out how to apply each one of those rate coefficients to each one of the initial concentrations. Well, each time through this loop, we have one value for the initial concentration. We can certainly add to this loop another loop to say for each one of these initial concentrations, we want to have a different rate coefficient. So I'm going to add another for loop here. And I need another index, but it's not this, in this case, it's not corresponding to a different concentration. It's corresponding to a different rate coefficient. So I'm going to call this RC index. But similarly, I'm going to create an index of integers that counts up from 1 to however long our rate coefficients vector is. So we've got this rate coefficient vectors. In this case, there's 3 values in here. So this particular for loop is going to start at 1, second time through the loop it'll be 2, and the third time through the loop it'll be 3. Now we need a curly bracket here because we have to delineate all the code that's operating within this loop with a curly bracket. As with before, I need to indent all of the code. I need to indent all of the code that's going to be within my for loop. So I'm going to highlight all of this code. This is what's going to be inside the for loop. Tab it over. That's because each time through, I want to repeat calculating my model, filtering out the values that are above 1% of the reactant remaining, and then store my results. So I need to do all of those things inside this loop. And these are what's called nested loops. I've got a loop nested inside a loop. And the way this works is the first time through this loop, I will then run this loop however many times I have rate coefficients. So it'll be the value of 1 for const index. RC index will be 1 the first time through this loop. Then we'll go through this loop again. This value will still be 1, but now the RC index will be 2. Then the third time through this inner loop, const index will still be 1, and the RC index will be 3. Then I'll finish this inner loop the first time through this inner loop, and I'll get to this outer loop, and this will change to 2. And once this is 2, this will be back to 1. We'll go through this inner loop 3 more times, 2, 1, 2, 2, 2, 3. And finally, this inner loop will be done. The second time through, we'll go back to this outer loop. It'll increment to 3, the last value, and we'll have 3, 1, 3, 2, 3, 3. And so that'll be the combined values of const index and RC index for this inner loop each time that we go through it. And that's going to give us this ability to generate results for every combination of initial concentration and rate coefficient. The last thing that we need to do, there's one more thing we need to do here, and that's make sure that each time through this inner loop, we are changing the value of our rate coefficient. So we need to have a rate coefficient without the s, it's a single rate coefficient here. That is our rate coefficients with an s, our vector of rate coefficients, indexed by our RC index. So just like we have to change our concentration, initial concentration, according to our concentration index each time through the outer loop, each time through the inner loop, we need to change our rate coefficient according to our rate coefficient index. finally, we need to make sure we have our data structure set up so that we can keep track of all of these different results. Right now, we're only keeping track of the different concentration index, and we need yet another layer of our results hierarchy to keep track of the results for each change in rate coefficient. So right now, I'm creating a first level of this results list based on the number of initial concentrations, but for each one of those initial concentrations, I need another level of results indexed by the concentration index. So I'm saying for each element of this list that I created before the outer loop, and for each initial concentration, I need to create another list for each one. Within each one of those elements, mode equals list. And the length of this needs to be however long my vector of rate coefficient is. So just like how I had to make this outer list, however many elements I had for concentration and initial concentrations, each element of this list needs to be a list that has as many elements as there are rate coefficients for each time through this inner loop. So my whole data structure is now set up, and the idea of this hierarchy is we're adding another level of the hierarchy. And that means each time we record a result for each concentration index, we need another layer of index here where we're keeping track of each different rate coefficient for each different initial concentration. So now I have a nested loop that's creating a nested hierarchy of lists. Let's go ahead and run this. Looks like it ran, so I didn't have any bugs. And again, we can look at our results. There's a couple different ways we can look at the results. We can either just type it in here and look at the hierarchy. And if I scroll up, there's going to be a lot more data in here now because we've had this nested loop. So here we are starting at the first element. There's going to be a 1, 1, and then a rate coefficient, a concentration in it, times const filled, all for that first combination of 1 and 1, corresponding to a rate coefficient of 0.05 and initial concentration of 25. Then we have a initial concentration of, I had that backwards, sorry, initial concentration of 25 and a rate coefficient of 0.05. Then our second time through the inner loop, we'll have 1, 2. That means our initial concentration is still going to be 25, but now we've moved to 0.1. And we can also look at this with our viewer. So if I click on results here, it's going to do a capital V view of results. I can see I still have this outer layer of results that's going to be 1, 2, and 3 corresponding to the initial concentrations. But when I look at one of these, I see now that there's now another layer, 1, 2, and 3, and these correspond to each different rate coefficient. So for 1, 1, that's going to be an initial concentration of 25, a rate coefficient of 0.05. For 1, 2, I'll have an initial concentration of 25, but now a rate coefficient of 0.1. And for 1, 3, I'll have an initial concentration of 25 and now a rate coefficient of 0.2. And if I go to the second element of these overall results, now I've switched the initial concentration and I'm going back through all the different rate coefficients. So 50.05, 50.1, 50.2. So this is how nested loops work and how they can build a hierarchical data structure of our results that gives us a full factorial combination of initial concentrations and rate coefficients in our sensitivity analysis.